Right. Just before I start, as a father and being spoiled by my kids today, and I can't walk because of the amount of food they stuffed in me. I hate Father's Day. Anyway, how you doing, everyone? I hope everyone is good. Long time no see. Well, I wouldn't say long time no see because I have been. Well, I've sent the last video a couple of days ago, so I'm a little upset today because I did record this video that I'm actually re-recording now at 3 a.m. This morning, and unfortunately, after I finished recording, I realized I wasn't recording. You know, interesting. Right, so we're going to start now working on the OMAP today. And today we're going to talk about how to interface between Mr. OMAP in here. As you can see, so let me just get my tweezers. So this is the OMAP, as you know, here. And we are going to talk to the Arduino board on that side. So this is the Arduino board. Just say hi. Hello, Arduino. And here is the OMAP. Hello, OMAP. Yeah. Right, so I'll get on the hardware setup that you need to do first before you do any of that stuff, and why would it not work when you're going to try to attempt to do this first time, and how to resolve the problem. And also we're going to touch on today, so just giving an index on two versions of the serial communication. So we'll do the chips version and we'll do the salad version. Yep, you heard me right. The chips, the fat, and the salad, the healthy. And you'll understand what that means in a minute, or in as the time comes by. So let's get started on this one. Initially, as you can see, that's the OMAP, and we have this little chip here. Oh, sorry, let me just make sure my hands are not in the camera's way. This little chip down there is the black, the middle of it is actually the OMAP itself. You can see there's a lot of things connected to it. So you got a video interface, an audio interface, and here they use the AIC3106, which we don't really care about, and eventually going to replace with the same thing used in another music instrument to get the data and stuff working. But forget that for now. The issue we have with this board now, as you can see, the OMAP is a BGA chip. BGA chips means the pins are actually at the bottom. And just to show you what an OMAP from the bottom looks like, let's get the stuff I have from Texas Instruments. So these are all CPUs and processors and whatnot. And that's an OMAP chip in here. So an OMAP chip, my friends, is this. And you can see that now. It's got about 21 by 21 array. That makes it over 400 pins. So with 400 pins down there, and you can see how small this is, probably even smaller than this one because this is used in mobile phones today. Anyway, let's carry on. So what I mean by that is, if you want to interface with the outside world, there's two ways to go. Either you would find which pins connected at the bottom of this guy, and where are they interfacing with, i.e. where is it connected on the board? How can I solder something to it to get it to work? Or the harder version, which is to make your own board, map everything out, which I already have, and find out where the thing is, and then map it this way. But today we're going to focus on this board in here. So luckily, I managed to find where the pin goes. So what we have on this chip at the moment, we have three serial connections, serial ports. There are three. There's UART0, UART1, and UART2. UART2 we're not using because we don't need it. UART0 is probably mostly for the system, and we tend to use it mostly for things like the printer, the UART printer and all that kind of stuff. We're not going to use that now. What we're going to use, we're going to use it internally, but there's something else. But what we're going to use mostly is UART1. And UART1, after debugging and tracing and all that kind of stuff, the pins for UART1, if you are interested to know, they're actually, if I'm just going to turn this upside down, the OMAP in here, they are based on, just going to take my tweezers in here, and I was going to show you that now. So you've got these two connectors in here. So you've got one long connector and one next to it. This first long connector is the EDMA stuff. You really don't want to touch that at the moment. Just leave that alone. This guy in here is what we need to interface with. The combination of so you got another one here we're not going to work on, the small ones. So these things in here are mostly for, what's it called, the LCD to connect. So if you have an LCD screen, a touch screen, just hook it in there and it should just work. But there's a lot more to it than just an LCD screen. So as you can see, there's a lot of pins in here. It's about 63, I think, if I remember correctly. But in here we have, after tracing, the pin before the last. So you see this connector in here, this going that way, on the left hand side, let's just say. At the bottom of it, the second pin from the bottom to the right. So we're talking about this guy here, there. You see what I'm pointing at? I hope you can see it. So this here is the ground. So ground pin, we're going to connect a black wire to it because it's ground. Ground is black, I always do black. Right, so that's the black wire. And then we have I'm going to choose a red color for the connection. Go away. Yeah. So red color for the signal, which will be held on pin number 10 on the same row, or same column, sorry. So this is the second column, so 1, 2, on the same column of the ground. So you got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this is the guy we need to hook into. So now, just going to double check. So we got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that's the TX, and underneath it is the RX, and then here we have the ground connection. So that should hopefully be enough to work at the moment. Yeah. So this is fine so far. So now we connected this stuff. Now, when you connect these things, you would expect that to actually work, and when I fire something out, I'd expect a signal. I expect to see some signal somewhere. So this is the hardware setup, and what I have in here, I've actually hooked this up to my oscilloscope. So the oscilloscope in here will read the stuff, and you can see that pink line down there. Hopefully, yeah, that should give you enough indication of what is happening going at the moment. So yeah, I mean this setup by itself should be fine. Now, when I go on the code, so if I'm just going to quickly glance at the code and then I'll explain it in full detail. So just bear with me in here. So if I look into the code itself at the moment, you will see that I have, actually, let me just take my picture off there because it just makes it easier. Yeah, I think part of the things wasn't recording yesterday is because I think the CPU got overloaded, but that's fine. Right, so we have the standard stuff, includes stuff. So you've got standard IO, strings.h, these are standard C++, or C libraries. And you've got the sysbios, the board, the UART driver. The CSL stands for chip support library. It can be good and it can be a nightmare sometimes. I'll explain why in a minute. And these two guys here, the GPIOs, we're not using at the moment, but I always keep it in there just in case I want to turn something on or off from a pin perspective. So these are not required, but so all you need is only these. Hopefully, you know, I'm really hoping that the screen quality is not that bad, so you guys can actually read what I'm actually pointing at. So now, buffer is the buffer we need for communication. You could be more clever and then do a read buffer and write buffer, that sort of thing, if you like. I mean, transmit and receive buffer, that sort of thing. But I think one buffer for me is, you know, is good enough. That works. Counter in here is a global variable. I actually count the stuff. So it starts from 0, and then whenever a function needs to access it, it'll increment it by 1 to say, you know, 1, 2, 3, etc. And you can see that here. So you got my thing looping down there. It's, you know, it's doing something. You can see that counter. The counter is actually in hex. I like hex. I hate decimal when I work. So I always do. I'm a hex guy. Yeah. So now, as you can see, I have a TSK, which is a task. I always put 3 letters to indicate what thing I'm actually looking at. So that's a task, and there's a UART loop. So the UART loop is very simple. You know, it just a few lines. So it ends at line 81 and starts at line 19. So it's about 60 lines roughly, which is okay. So in here, as you can see, we have bytes read and bytes written. So how many we read from the serial, how many we wrote back, sort of thing. And here is one of the crucial elements you need for your stuff. But if you look at this, don't be intimidated by it. This is a setup block to set up your serial connections. As I said, we have serial 0, 1, and 2. At the moment, we're going to set up a serial. It doesn't matter what serial, you know, serial could be serial 50, but now that is just literally feeding parameters for the serial connection. So initialize in here, UART initialize. We're initializing the UART, Universal Asynchronous Receiver Transmitter, UART. And we are, you know, defining a params, UART parameters, so params in there. And on this line here, you can tell we are actually telling the CPU or the OMAP to tell us what the parameters are. So the standard default parameters will be stored into this thing we just defined. So these 2 lines are basically to define UART parameters and fill it up with whatever the system thinks is right. Then we're going to overwrite this UART params with all that stuff. And what that stuff is, standard serial connection. So the standard is baud rate. So we're defining, you know, 115/200 as baud rate. Data length, you know, 8-bit data length. 1 stop bit, no parity bits, and in here the read return mode. Don't worry too much about those for now. You don't really have to set them up, but I do myself, and the reason because I'll explain these in a minute. Don't worry too much about that yet. But just moving on from all this, the callbacks I'm actually put as 0, i.e. nil, so we're not having any callbacks on this one. And I like to do binary transmission and receive, even though it's all text, but I still like to call it binary. And timeout, it'll just, if I'm using blocking, which means if I call a function, it'll block until there's a data. Once there's data, it'll come back to me saying yes. Here you go. So and it will wait forever. It'll just not going to wait until a certain timeout. So you can replace this with a number if you like to wait, for example, for 5 seconds, and then it'll say, yeah, I can't do it. So all that stuff is just to set up a serial port. Now, moving on, and here we are opening the serial ports, and here is where the magic is happening. You remember we said UART 0 and 1 and 2. We are opening UART 1 in this case. So UART 1, we are opening with these parameters. So I hope that makes sense. It's literally we're telling the system, please open this port and use these parameters for that port going forward. Yeah, and that open function will return a handle. Handle is a number to say yes, it's been opened. Here's the ID for whatever we opened, and then we move on. So if the handle is up and running, if we generated a handle, then say yes, open successfully. Otherwise, if not, it will just crash and die. I'll say yes, sorry, can't open UART, and then it dies. That's it. And afterwards, once the handle is actually open, as we said earlier, it will, while one means an endless loop. It will just keep looping forever. And I actually remarked this code intentionally. I'll explain that in a minute. So the only code working in here is these three lines. And what that means is I'm actually creating a variable called buffer. We talked about the buffer, the send buffer or the buffer earlier on at the beginning. And I'm filling that buffer with the following. I'm just saying looping, colon, 8 digits, hex, with the variable I. I is the counter. And actually, I should say here, counter. And in here, I just say here, counter. That makes more sense. So we're not using I at the moment. As I said, we're doing the counter for that reason. So take I off, and I'm just going to replace it with counter equals 0. Actually, yeah, that should be fine. That should work fine. Yeah, so that loop in here, what it does, it fills the buffer in with this text that says looping 00001 or 02 or 03, that sort of thing. So just keep displaying this looping stuff, as you can see it there, just counting as you go along. And then every time it sends it across, so it's got UART write, so it's writing it to that handle, i.e. UART1, and it's using that buffer that we just created in here, or just filled it in here, and then it's sending as long as this text is. So if this text is 10 characters long, it'll send just 10, and then it will wait for about 1,000 milliseconds. So that's 1 second every time it sends something, and as you can see, it's waits in here on these, wait 1 second, and it keeps going on. And then it increments the counter, and then it'll keep looping. So in a nutshell, that's what the code does. And if you want the essence of it, I mean, read my previous videos on how to create a task. I'll just quickly touch on that. So the main function, how it starts, it will say, it'll print something out. It'll say, yes, UART starting. This is a remark, forget that, that's something I'm actually doing else. We initialize the board with the pin mux. The pin mux basically mean, the OMAP chip I sent you, I just shown you now. This pin mux is a preset configuration to say, yeah, for example, pin 5 is an output and it uses this voltage. Pin 6 is an input and it uses that voltage. Pin 3 is a clock, and pin 200 is whatever. So that is a configuration. You don't need to worry too much about that. Just imagine this is the initialization of the board itself. So this is where the board is. And then the module clock, we initialize that too, because the board, I like to do that over time because it's got a clock on board, and every time the seconds tick, you can set the hours and seconds and minutes and date and time, and that will just tick. We're using this because we're telling it to initialize. And here is the most useful one for us in this example. So we have the board UART standard I/O. We are initializing that too. So all these three are ORed together or added together to produce this board config. Once that's done, it will initialize it. So the board will be initialized using those three variables. And then it will say, if you can see this, then it's fine. And then it will initialize BIOS start. BIOS start is something called a blocking function. When you run this, it will block. It will wait indefinitely in here because it will just go into the BIOS. And the BIOS is here. This is BIOS. I don't know if you've heard it, if you've seen it. I've explained this is BIOS in previous videos, so please refer to those if you like. So quickly, we're going to touch on that. We have a task on the sysBIOS created, and the task fires this function, which is TSK UART loop, the one I just literally explained. So TSK UART loop will be powered up once the BIOS is up and running. So if the BIOS is up and running, we expect to actually fire this up, and then as I explained it, it should work. So quickly running it, the I, we removed, we replaced the thing with a counter. And because we removed that, the counter in here, we took I off, if you remember. So now it should be counter. Yeah, that should be fine. Sorry. Let's just do that. And it should just compile and work. Just wait. Yeah, it's linking, so it's good. Clear screen, clear scroll block. Brilliant. And now we should see that box coming up, and this should just compile and run. Yeah, so now you can see that here. Serial data is working. You should see this in the console. UART is open successfully, so that's the function. So this is here. That line actually worked, and you can see the handle is there. And now it's looping from 0, and it's just carry on. So that opening is successful. And technically, I should be seeing, because we have in this function in here, by UART right, I should be seeing something coming up on this line, on this pin 10, but I don't at the moment, and the oscilloscope is actually all down. Now, you probably ask yourself, what exactly is going on? Why am I not seeing this? Is mainly because TI, or Texas Instrument, has actually blocked this, and in manufacturing they kind of removed the secret sauce, to call it, to make this work. And I'm just going to touch on that and explain exactly what's happening. As I said, the 400 pins goes on all over the place on the board, meets all over, lots of stuff in here. And then before it gets to this guy in here, it should go into a 0K or 0 ohm resistor, or a fuse if you like, or a really tiny hairline resistor. And that resistor is used to allow the CPU to go to these two pins or not. So what we'll do in this example, I'm going to solder, using my microscope, I'm going to solder two resistors, R206 and then R209. And if you bear with me now, before I do any of that stuff, do not touch anything with a soldering iron unless you disconnect it from the mains, especially in the mains, and any other connection. Otherwise, you could have, the soldering iron could have the tip connected to the ground of your mains power, and that could actually send so much power and then kill the whole board, or even burn it. So never ever solder anything that is connected to the mains. Just wanted to let you know. I'm going to explain to you, or prove to you, that the R206 is for TX and R209 is for RX. And notice I've got everything connected, and the oscilloscope, as you can see down there, is actually in pink. It's got this line like this. Notice what I'm going to do. R209 is this one. I'm going to touch the pins of it here. So touch those two. 1 second. So 209 goes there. Yeah, see that now? You see this? I don't know if you can see it. There. See the clock? So I'll leave it there. I'm just going to, get the camera, or get the iPhone closer. Just going to use my iPhone just to show you what's happening in here. So if I take the iPhone, so what we did, pin 209 is actually here. So these two guys, and if I hook it up like this, let me hold the tweezers correctly. That's right. So yeah, there we go. So now you can see on the oscilloscope, I've got a signal, right? And that's the point. And so R206 is actually here. You can see it, and I just pointed out with my tweezers. It's actually, let me just do a 2. You can see that there. So 206 is this guy here, and 209, the other way around, is actually it should be here. This is the guy, 209 there. So 206 here, 209, and you can see that there. So what we're going to do now, we're going to solder these 2 pins, and once we finish the soldering, it should just work by itself. But before we touch anything, do not touch your soldering iron with the board if it's connected to mains or any other connection. So disconnect everything up first, then you can go and do the soldering. So let's do that now. So I'm going to power up my soldering iron first to 350. I like 350 usually. And I'm going to disconnect this whole thing up. So take everything out. Disconnect VGA, power. Take the 2 oscilloscope off. Take the debugger off. JTAG, audio out, USB and USB. So now, as you can see, I have released my motherboard, and we're going to now switch on to the other section, which is the microscope. So I'm going to put this here at the moment. Just turn my camera a little bit. You can probably see it there, but I'm going to use my microscope instead. And there we go. That's better. Just going to take my glasses off. Yeah. So now, where's my pins gone? There we go. 209 is there. Can you see it? I need to focus that better. And that's it. Good. You can see R209 is this. No, yeah, this guy. So R206 is this one, and R209, and also R205 does the same thing as R2, well, different thing to R205. So 5 and 6 do a similar job, but 205 is pretty much used for what you call an AES chip. And an AES chip, I'm just going to show you that here. You see on this screen that little thing on the corner where it's got all the pins and nothing in there. This is what the AES or the fingerprint chip is, and we're not using that. So R205 has been disconnected for that reason. Just save on cost. Didn't want to do it, but we're going to do R206 for sure. So let's get this thing started. And before we carry on, I need flux. Where's my flux? There we are. Good. So I need a little flux in here on 206. And also I need it on 209. Good. Okay. So that's in place. And now I'm going to, I need a little wire, if I can find something. Yeah, that's fine. That's good. So that's a little wire there. So I'm going to use this now. I'll connect this guy here. I need to also soak it in thingy. So do that first and soak it like that. So R206. Here we go. And I am now we'll have a little yeah, good. So 206, is that what we want to? We just need to short the pins. Yeah, that looks good. I'm good with that. I think I am fairly happy with it. Let's just make sure the other side is actually also done. I think it's good. What do you think? Perfect. All right, so that's one thing. So let's just cut the thingy off. Just making sure we haven't... yeah, I need to make sure this is all good. Yeah, perfect. Right, so we need to cut that off. Slightly, don't lift too much. You don't want to ruin... don't know if you can see that. Yeah, good. Come on. Yeah, so I think that's perfect, fine. Now the other side, we'll do number 2. We'll do 209. 209 is here. Can you see it? It's this guy here. So, same thing. 209. Wonderful. Okay, good. Let's go on. Solder the thing. Perfect. See that? Wonderful. And that's it. Let's just cut this guy. Beautiful. Now, before we go, we have to clean up with flux. Yep, I'm good with that. Yeah, sounds good. Okay. I just wanted to mention one more thing as well. You see, where is it? My tweezers. There we go. You see this guy, 2R206, and you got C209. Do not solder C whatsoever. Just be extremely careful not to solder anything with C. C means capacitor, and usually one pin of C will be connected to ground, the other pin of C will be connected to power somewhere, a power rail. And the reason we have a C there is to ensure there's no spikes in the power rail. So if you solder these two in as a C, you'll probably blow something up. So do not solder C, only R. So R206, we solder that in now, and R209, we solder that in too. So now the CPU, the OMAP in here, as you can see, this guy, the OMAP should technically connect to the pins in here on the outside. So now we're gonna start. Let's switch the thingy off. The what do you call it? The solder iron. Back to my glasses. We don't need the microscope. Thank you very much. Now, thanks. You helped a lot. We do it a few minutes. We solder this in, and let's return into the E-bench now. Perfect. And now we're going to start reconnecting stuff again. So now we connect the power last. So first things first, let's get the VGA up and running. Yeah, so VGA is there. Power is last, as we said. Just tidying things up, really. Very good. Power is there. Okay, get the keyboard back. Okay, so USB out. Yeah, so now we have at U-boot prompt again. So now we have the let's just get the thingy just to point again here so that we can see what's happening. Yeah, so that is now. Yeah, good. So now we have the thing back up. It's working. We don't know, well, the board hasn't been blown up yet, so that's perfect. Good sign. And now we're going to turn it upside down. And as we said before, pin 2 from the last, we connect here. So hopefully you can see that. So pin 2 from the last on the second connection. And then pin 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Right? And now the thingy is connected. The oscilloscope is doing some stuff, but it's not there yet because literally we have not loaded our code yet. Because when you reboot the OMAP, you lose the code again. So what we'll do now, we'll just fire up to recompile. So now we're going to upload the code again. We're waiting for that thing to load up. So yes, now it's loading up here. And it should come up any second. There we go, that's the loading here. So now we're going to go back into the eBench and look at that. See? And that's exactly what I mean. So now you see that thing is actually dancing. This is the binary counting. So if I just zoom onto it now, and then just take you to that signal itself in particular. Zoom more. Yeah. Yeah, see that? Do you see it? Let's just, zoom on. There. See? Now you see that thing is counting. That proves to you that actually this thing we just did works 100%. So now we know we can talk outside world from the TX bit. So if I say anything to TX, I'll be able to see it in Arduino. And this is part 1 of the equation. So now we can send something out, but and the receiving. So 206 we solved it is for the outgoing. The 209 is for the incoming, for the receiving. So now what we're going to do is I'm going to, you see the Arduino is actually blank, nothing in it. Is just no code loaded up yet. So disconnect the oscilloscope now. We're done with the oscilloscope, so thanks for that, Mr. Oscilloscope. We're just going to shut you down as well. Perfect. So that's done. And now we're going to carry on focusing only on the OMAP side. So hopefully that should be more clearer to see, hopefully now. Yeah, now we can see both. It's fine. I think it's good enough. It'll work. It'll do for now. So now what we're going to do, ground goes to ground pin. Let's take these, this one away, the debug. So ground to ground pin. And we've got Mr. This is a TX, so that's transmission or transmitting into a receiver. So TX, RX, TX, RX, so number 4. And we're going to do the number 3 for the TX for the other side. And I can tell you this goes to the one before it. I know I should be using different color, but it's fine. So now we are set up. So ground to ground, you have to set the ground pin up. And you got TX and then RX going back and forth. I hope that makes sense. So now we're going back into the screen capture. Yep. And now we have set up this thing fine. It works good. And now I need to do go into Arduino. In Arduino, you can see, I actually wrote this code. It took me about 10-15 minutes. You can see is a very small code. All it is, similar thing. We have a counter on Arduino. Setup means run only one time just to do just to do things for the first time in your life. So we are telling it here serial.begin, which means the console. Let me just show you the serial. So tools, serial monitor in here. If I power that up, I get this guy in here, starting up there, and I'm saying to it, when you run, enable that serial. So I want to log stuff to see it on my serial console of my Arduino of my PC. And serial 2 is where we connected the wires to. So serial 2 is where the wires are going on the OMAP. So TX and RX going to serial 2 at the moment on the Arduino. So also running on at this. So this is the baud rate 115200, similar to the one we said we're going to use actually here. So we are defined 115200. Make sure the baud rates match up on both sides. So this is 115200, is 115200. Default also length 8, stop bit 1, no parity. Arduino uses that by default anyway. And it will print out a message to us to say, yes, I'm starting. And the loop is very simple. Loop basically in Arduino means it's just going to keep going on and on and on the same thing. So serial 2, if it's available, that means if I receive data on serial 2, on the, i.e. coming from the OMAP, then on this guy, print a blank line on my window in here, and print also another line that says I received something, serial data received, and then print again whatever serial 2 has data-wise. So serial 2 have some stuff. We're going to read it as a string. Read string sometimes can take about a second to finish. It doesn't matter. We're just going to treat it as what we need to do, and it will print it out to this line. So whatever the OMAP is going to say, we're going to display serial data received, and I'm going to dump it all onto this window. And once that's done, this condition will work only if OMAP is sending us something. Either way, regardless of this whole block running or not, regardless if we received anything, we are doing a ping kind of heartbeat to the Arduino, to the OMAP from Arduino. So what we're saying in here, we are printing in here, sending from Arduino. We are writing to serial 2. So we are sending to the OMAP a message that says, I'm sending you something to Mr. OMAP, and I'm sending you the counter value. So it'll be sending from Arduino 1, 2, 3, etc. And on this screen, I'm going to be outputting dot, so I know there's something going on. It's just like a one of those hourglass window download kind of thing. So I'm just going to dot. So now actually I've been pinging the thing to see if it goes live or not. And if it's over 50 with so many dots, I don't want the screen to just keep going this way. I want it to, every time it reaches 50, it just go back to a new line. So every time it goes to 50 characters, 50 dots on the screen, it just creates a new line, and then reset the counter back to 0. And this is going to make the Arduino sleep for about 1 second, 1000 millisecond, and increment the counter. So it really is simple. All is in layman's terms, it's going to ping the Arduino every 1 second, and it's going to ping OMAP every 1 second, and if OMAP have something, it will show it to us. So if I'm going to run that code now, so now I'm uploading to Arduino, as you can see down here. So that's loading up now fine. And now we can see I'm sending something down to OMAP, and OMAP actually is responding. So serial data received looping from OMAP. And I mean, it's working. And so far, so good. I'm quite happy that this whole thing is working. So now we have literally established a communication between Arduino and the OMAP. So now every time, what we're seeing in here, Arduino is sending something to the OMAP, and the OMAP actually is responding back. Let me just check that. Yes. So now we have here, the following. So if I unmark this code, this basically is reading from the OMAP and displaying it on the screen. So, sorry, reading it from Arduino, whatever Arduino is sending. So right now, what is happening really is the OMAP is just literally sending stuff. So it's just sending looping and then stuff. So looping is here and looping, looping. So whatever we are actually receiving something. Yeah, so this is so far, as you can see. I'll probably have the lines duplicated twice to display, but don't worry about that now. What I'm just trying to say is OMAP is sending something to Arduino. And if I stop the OMAP, I'll prove it. So if I go back into OMAP and let me, if I just unplug the power, I don't want to do that catastrophic. Yeah, I'll do it. So I'm going to unplug the power cable from the OMAP. Done. Right? And now you can see it stopped. So I'm going to plug in the OMAP again, power up. But this time, OMAP, we haven't loaded up the code yet. So you can see now on the other on this screen, is actually stopped. So nothing is happening. And if I run my code again, but this time, before I run the code, I'm going to unmark these two lines. And the reason for that is, this is the other side of the communication. So the first side, without this thing that I just enabled now, I'm only sending from OMAP to Arduino. And with this bit in here, I'm receiving back from Arduino and then displaying it on the screen. That's literally what I'm doing. So I'm just saying read, and that read will will actually be blocking. What that means is it will, the minute you run this command in here, it will just freeze there until Arduino sends something out. And if we don't receive anything out, this whole thing will not even run. So for now, I'm going to, once we receive something out, if there's something received, it will just display it on the screen there and then move on. So if I run that code, yeah. Do you see that now? If I put these two windows together next to each other, you'll see this is the serial from OMAP. That's natively OMAP. And this is the serial from Arduino. And look at that, how nice this is. So I am actually now communicating back and forth between Arduino and the serial and OMAP. So this is the first, call it introduction on data communication between two devices. Now, I'm aware that this video is getting to 53 minutes long so far. And as I said before, I'm going to give you two versions, the salad version and the chips version. So this is the chips version. The salad version, I think I will probably actually, you know what? Let's carry on with this, because I think that's useful. People would love to see how the whole thing works, and I might skip some parts of the video to make it quicker anyway. So now, as you can see, we've got the thing to work, but if you notice on the code in here, so we're going to talk about the salad version. The bit over here, notice this guy is a while loop. And while loops usually executed by the CPU. And because the CPU, Mr. CPU will just run something and then do the stuff and then keep back and run it again. So you pretty much get the CPU really kind of tangled up and busy. And in example, for example, this line in here, it'll keep waiting until something happens, and then the CPU keeps coming up polling mode. If nothing is received, none of that stuff will work. it's not ideal how you should write your communication, because you really are tying up the CPU, right? And it's like, you know, have you seen Shrek? When they go to the kingdom of far, far away, when Donkey's sitting in the back and asking Shrek, "Are we there yet?" And then, "No." "Are we there yet?" "No." "Are we there yet?" "No." That's what's happening to the CPU. That's what you do into the CPU if you run this code. Yes, it works. Yes, we got stuff, transmitting back and forth between the two, but that's not a good common practice. And that's why it's called the chip. I call it the chips version. In here, if I would to write something better, in communication world, you need, this is called the polling mode. The other mode is an interrupt kind of mode. So if you just let the stuff do itself, and if data is knocking on your door, you just go and say, "Yeah, can you open the door for me, please?" It goes and opens the door, does the stuff, and then, "Okay, yeah, fine, I know, thank you very much." It's like that, and the CPU is sitting down comfortably, cool, having its own tea and coffee, and then doing the stuff, the wonderful stuff, while others are helping. The others are interrupt, DMA, and stuff like that. So in this section of the video, we're going to talk about an interrupt, or called the callback of the function. A callback is an interrupt. It only happens, and you can see that there at the moment we are having it as 0. When we run something up, we want the callback to be up and running, because when you send something to the the system, you want it gets in there, it gets quickly acknowledged or fired up or acted upon without the CPU doing much intention on it, and or much interaction on it, if that makes any sense. And then transmitting it back, same thing. Once it's transmitted, then the CPU gets an interrupt. "Yes, I've done it." "Okay, thank you very much." You can have. Rather than the CPU standing up, moving on, doing something, and going and sitting down again, it actually asks something. "Yeah, can you DMA? Can you interrupt? Can you just go and see what this guy's is all about?" It's that different. So it's like someone helping the CPU. So now, going back into this guy in here, I now have the task UART asynchronous. And this is the guy we're going to talk about. So I am going to my BIOS again, and rather than having that task UART loop function called to do the stuff you're looking at, I am going to paste my other function, which is UART asynchronous. And that is a different function now. So save and run. Okay. Now, you probably see I'm not going to be displaying much things onto the OMAP for a very good reason, but you'll see the Arduino will still be logging some stuff. So let's just clear the output in here, and then clear the output in there. Okay, and wait for this to upload and finish. There we go, loading. So that's pausing now, and that's pausing too. See the dots? There we go. So now you see the message is different. So reply from OMAP. So now, rather than seeing this thing on top, you're seeing differently messages because I'm using a different function. But this time, I'm not displaying anything in here. It's only this guy silently is doing some stuff, and whilst this guy's sending something, this guy's actually reading it back. And if I go back into here, there, and I'll explain the function now. So this function is exactly what we said, similar, the way we set things up, but slightly different. So the callback now, I have this UART read callback and UART write UART1. So these two read and write callbacks I'm actually allowing, and rather now than having the previous mode, which is blocking, I'm actually now having the callback thing. So either callback or blocking, we have it there. So read and write mode is so callback and then callback. Perfect. And in this one in here, I'm going to print the two messages in there. You can see them here. So these two are printed nicely. And then I'm just going to say UART read. UART read in this section, because the read type in here is a callback type, it's not a blocking function. What happens is it's going to execute, run once, and immediately get the callback to wait until something comes up before it says, yes, here it is. So that's literally it. So now it frees up the CPU. So that's just going to continue. Nothing is waiting. CPU isn't waiting anymore. It just immediately executed and told the UART of the interrupt, yes, interrupt, go handle this and wait for something to happen. And now because we have this, the byte read, it's not really byte read, but it's like a successful status. It'll say yes, listener started successfully, and you can see that in here, does as the last line. And then you can see that now I'm just having a huge delay, or a huge, call it a, let the CPU sleep for now. In other words, the CPU, literally, this command does absolutely nothing. Literally nothing. It's just sleeping. It will not even care or do anything whatsoever at this stage. That's what the delay is, just sleeping it. So I'm sleeping it for 1,000,000 seconds, 1,000 seconds at the moment. And that's it for that code. And if you look when we read, because we define the function in here, so the function, we have the callback there, you can see it. So the read, what happens is, remember as I said, I'm not displaying much in here, I just remarked those two print lines. And what I'm saying in here, if whenever something comes up, this automatically will be triggered. There's no ifs and thens. It just immediately comes in here and then say, yes, I got something for you. And then I am just, playing about, saying if the counter has not reached 5, then just do normally, reply back to say receive from OMAP and give the counter, and then fires it across. And if not, I'm just going to read without that. So what I mean by that is, if I just take the auto scroll off in here and go back into number 5, and you'll see, let me just rerun the code, clear output, run the code again. So I want to show you what 5 is. So 5, I'm not logging, I'm not sending reply from OMAP. I'm just doing 1, 2, 3, 4, and then 6. And you see that now. So once this is loaded, you'll see in here on that screen. So clear again, waiting for that thing to load. Anyway, so when you write something up, you do the UART write. Once UART write has finished, it triggers this interrupt again, and that interrupt will run this read command again to get it back into a read mode. So, and then the CPU goes do nothing again. So you can see those two functions, really simple. One of them will either fire a write command and then wait indefinite. Well, it doesn't wait, just wait until something happens, or sit down until something happens and then get triggered by it, or not do much and then it'll just, rather than writing something back and then reread, we'll just tell it, yes, okay, just go and read something up. Maybe if I simplify this a little bit, if I remark all that stuff up so that you understand exactly what's happening in there. Yeah, so what I have in here, so to simplify the code, if I just put these two lines instead, so forget that whole counter thing. What I'm doing in here is I am actually making the string, building it up using the sprintf into buffer, and then firing buffer across to get to the other side. Literally, simple as that. What I'm trying to say onto this command in here, if I just do this, it probably won't work. What happens is it will write the stuff. Once the writing has finished, it automatically triggers this callback function because the writing has finished to the serial, and then it will say go and rerun the trigger, the reading trigger. And when you do communications like that, you always must make sure that you trigger the UART, the reader function, once we finish starting. The thing is, you cannot trigger the read function if you are doing a write at the same time. And that's why I have this kind of isolation to say, if there is something to write, then write it across. Or if it's 5, then write it. If it's not 5, then just do the reading itself, right? So, I don't know, does it make sense? Am I talking too much? I'm sorry if I am. Let me unmark the code and do this one more time. So now you'll see, I think when I saved it, it actually built it, and then now you see the Arduino having nothing output. So I'm going to run the code again. This time I allowed it again. So notice counter, it'll say 1, 2, 3, 4, and skip 5, and then 6 and 7 and 8, that sort of thing. And what I mean by all this is, if you don't intend to send something out, just make sure you trigger the read function. It's really that simple. And now I should see Arduino login stuff on that section very, very soon, hopefully. Yeah, so now we're receiving this. So I'm going to say 1, 2, 3, 4, no 5, see, 6, and then 7. And that's exactly what I'm saying. So 5 has been dealt with, but it's just sometimes you have a command that you don't want to send anything out. But if that is the case, then just make sure you trigger the read. The rules are, I'm trying to say, you cannot trigger read at the same time if you just send write until write is finished. And because of that, you do the write, and then that command, the read, has to be at the end of your write callback so that it's asynchronously do the stuff. So now I can write a whole kind of, hello, a conversation between two devices to say, hello, how are you? Yes, I'm fine. What's the weather today? It's sunny. It's just keep bouncing thing back and forth, and without the CPU doing any interaction. Literally, it's just it's all quickly bouncing back and forth. And I hope that video makes sense into how you communicate between your OMAP and your Arduino. So that's my first video on communication to the outside world. Now, that said, I need to really clarify one thing. Why on earth you have an OMAP card and you would still use a small thing like Arduino to actually drive it across? Does that not remind you of something? I'll touch on that again. The Kronos at the moment uses a PC to communicate to OMAP to tell it to do more sophisticated stuff. So think about it. I have the OMAP set up, and I have all the sophisticated sound cards and video modules and all sorts of stuff that are really required some really muscly fast processor that does so much stuff. But excuse me, sometimes you don't really want the OMAP itself to do that kind of thinking about, press this key to do that sound. You'd rather have the OMAP kind of listening to say, yes, I am ready to do whatever you want me to do. What's next? So that can be done either by connecting something like a PC or Arduino to the OMAP and telling it, yes, I want you to run this command and then do some stuff. And that's what the PC is doing to the Chronos using USB, but we are doing it on a slightly smaller scale version by using an Arduino rather than a PC, talking to the OMAP via the serial port and telling it to do stuff. Now, that stuff has not been there yet because we haven't done any videos yet on other devices like the AIC 3106, or the audio, the video, the VGA, that sort of thing. And in other words, or to add to that, okay, then why don't you use just an Arduino? You might ask. Well, no, you can't, because Arduino, in its glory, with this mega Arduino, in its highest ever state, it's only a 16 megahertz board. The OMAP, just to give you a magnitude on this, the clock that runs the sound card on the OMAP, which is considered a very tiny thing in the OMAP's head or hair, is 24 megahertz. So 24 megahertz just to run a little bus with clocks to output sound or do I2C and that. So Arduino can never ever cope with this. Arduino is 16 meg, and that's it. That's the limit for it. Arduino nicely used for serial connections, little buttons, little sensors, little things. Communications fine, but not for that magnitude or that level of intensive processing. It does really require a beefy processor, and this is where the OMAP comes in. Now, this OMAP board or this OMAP CPU is what, minimum 6-7 years old. The one used in Chronos is the 1808, which is the 12 years old. The later big brothers are much different. Take this one, for example. So this is the 5728, the OMAP, another OMAP, or another processor, and that's got a touchscreen. It's got a lot of stuff, and it's got a huge lots of things. So if you think this OMAP is sophisticated, this is at least 10 times more, because it's got multiple cores, it's got many things. So rather than having Arduino talking to it, you have more than one core talking to each other. So one core will do something, and one core will do the thinking, one core will do the muscle lifting. So you can pretty much power a whole music instrument, with just that AM5728. And obviously, the more we go by, the more time we progress, the more intelligent devices will become. And yeah, so I hope that that kind of makes sense. I hope it kind of explains how this whole thing works. So yeah, I mean, this is what I wanted to really show and talk about. Hopefully, it gives you an idea of what's, of the capabilities of what this thing is, does. And I'm hoping to progress things further as we go along. It's just I'm actually going to be busy. I've got something to do, at least for the next few days. I hope that thing kind of explains what's happening. So I'm gonna end the video there. It's about 1 minute 16 seconds, or 1 hour 16 minutes. I'm gonna try to cut it down as much as I can. Thank you for watching, and have a lovely day. Thanks, and talk to you soon.